This is Derf Sites. This functions tutorial is on transformations of functions. This table shows the various transformations we'll be examining, and our function will be named f, y equals f of x. Remember, with functions, the y-axis in the xy coordinate plane is the second coordinate of the ordered pair, and it has the value of the function at the independent variable's value x. We'll be looking at shifting a function up or down vertically, left or right horizontally, reflecting a function across the x-axis or across the y-axis, stretching and compressing it vertically, and stretching and compressing horizontally. The simplest starting point is a vertical shift up. We start with the function f of x equals x squared, shown in blue here, with its vertex at the origin. Replacing it with a new function, x squared plus 2, the difference being that we've added 2 to the entire function, we get a vertical shift up. Every value moves up by 2. And the entire graph is shifted vertically up by 2. The next is a vertical shift down. Here we start again with the blue x squared, and the related transformation is shown in green, x squared minus 2, subtracting 2 from the entire function value, moves every point down by 2, translating or shifting the entire graph down. Next, we have horizontal shift to the left. We start again with x squared in blue. This time we take x, not the entire function, but the independent variable x, and replace it by x plus 2. And our new function is x plus 2 squared, shown in green. It initially seems counterintuitive because we had x plus 2, but remember, we're not adding 2 to the entire function. We're replacing the independent variable x by x plus 2, and it results in a horizontal shift of the graph to the left by 2. Next, horizontal shift to the right. This time we take the x and replace the x by x minus 2. Again, not what you would normally think of with the minus 2, but remember, it's the x, not the entire function, and it ends up shifting it to the right by 2. Let's consider for a minute why these horizontal shifts seem to go the opposite of what we might hope for. Why is the direction, left or right, of a horizontal shift different from the replacement sign, plus or minus, of the independent variable x? Let's start out very simple. Consider x equals 5. X equals 5, the graph of that is a vertical line that goes through the x-axis at the point 5, 0. It's a vertical line. Let's take x and replace it, just x, by x plus 2. Then we would have x plus 2 equals 5. If we subtract 2 from both sides of this equation, we get x equals 3. So we started with the vertical line x equals 5, and after replacing x by x plus 2, we ended up with the vertical line x equals 3, which is the original vertical line shifted left by 2. Next, let's just consider a table of values. If we look at x squared for each x, if x is 0, x squared is 0, x is 1, x squared is 1, 2 squared is 4, 3 squared is 9. Let's compare this now to x minus 1 squared. We've replaced x by x minus 1. Well, if x, let's see what we get here. To get the same values as x squared, the 0, 1, 4, and 9, that would happen for x's of 1, because 1 minus 1 is 0, and 0 squared is 0, and 2 minus 1 is 1, and 1 squared is 1, and 3 minus 1 is 2 squared is 4. So we see here that the same values occur, but look where they occur. Note that the same function values occur when, in the second function, x is 1 larger, or 1 to the right, than in the first function. Therefore, the second function is the first function shifted to the right by 1. So we've seen some intuitive understanding of why this happens, but we can just remember it now. If you replace x by x plus something, it shifts us to the left. X by x minus something shifts it to the right. Next, a reflection across the x-axis. We'll start with the function in blue here, x squared plus 1. And if we take the entire function and replace the function by minus the function, that means every output will be negated. Every y value will be negated, and we'll flip it on the other side of the x-axis. And so we see here when we take minus x squared plus 1 instead of x squared plus 1, it's a reflection, a mirror image across the x-axis, simply by negating the entire function. Reflection across the y-axis. Here, we'll start with the blue function, x minus 2 cubed, and this time we're going to replace x, the independent variable, by a minus x. If you take every x and replace it by a minus x, so here instead of x minus 2 cubed, we'll have minus x minus 2 cubed. The result is a mirror image across the y-axis, a reflection across the y-axis. Stretching a function vertically. Here we have a function, the absolute value of x function. And the related transformation is simply 2 times the original function, taking every y value, multiplying it by 2. That is, taking the entire function and multiplying it by a coefficient that's greater than 1. 2 is greater than 1, stretches it, because the rate of increase is going to be more rapid. So green is a stretching up, a vertical stretching of the original function. However, if we multiply by a coefficient, in this case, of 1/2, which is greater than 0 but less than 1, it's a fraction, a proper fraction, we actually compress down the original function. As you see, it's squashed or compressed down. These stretches and compressions also can occur horizontally. Our original function here, absolute value of x, and this time we'll take x, the independent variable, and replace it by a times x, where a is a fraction, 1/2 times x instead of x under the absolute value sign. And this will stretch it horizontally, so it will stretch it out more horizontally. Notice it's the opposite here. The fraction value stretches it. The non-fraction value, when the coefficient is greater than 1 and you replace x by a times x, such as the absolute value of 2x, here this is a compression horizontally. Composition. These transformations can be composed one after another to get any kind of a great variety of related functions from a starting function. Let's look at this example here, where we start out in blue here with the original function 1, this square root of x right here. F2, our next function transformation, we replace x by x plus 1. That will shift it horizontally to the left. So we see the red is the blue one shifted to the left. Now we're going to take that one and multiply it by a coefficient of 2, which will be a vertical stretching of it up. We see this purple one here is stretched up from the red one. That's the third stage. The fourth stage down here will negate the entire function, take minus 2 square root of x plus 1. That reflects it across the x-axis. We get this brown one here. And the final stage will add 3 to the entire function, which will shift it up vertically by 3. And this green line here is the resulting composition of all these different transformations. So in summary, we have looked at these simple transformations that allow us to greatly enrich our portfolio of functions by taking simple origin-centric functions and moving them around and reflecting them or stretching or compressing them, and also allowing us to, when we see these other kind of functions algebraically, without initially seeing their visual picture, we can isolate their fundamental starting point and how it was progressed to where it should be.